What's up guys? I know it's been a little while since I made a video, but I finally had some free time now. This project that you're seeing here, I seriously thought that I had released this a long time ago, but I guess I didn't. I think one of the main reasons why I never actually released this project, I remember putting up some files on Pastebin on some of my previous videos that actually utilized this project. But I think the main reason why I didn't release this project was because the saving system was actually saving to a MySQL database, but I knew that most people would definitely not have some kind of like an Apache server running which would take like the genome information of the best creature and save it into a database or query database for those kinds of things. So I've just completely changed the saving system now to actually save to a file, which is, I mean, I don't know, it's okay, I guess. The Unity project will be in the description below. I'm just gonna showcase some stuff that I've done with this, and they're actually pretty damn cool stuff. Some projects you've already seen in my previous videos, another new project that I worked on recently. So what this project is essentially, suppose you have a problem, for example, a pole balancing problem, you know, where you have a pole on a cart, you want to balance it. That's just as an example. Without having to worry about how the algorithm such as neat works, you could just create an agent and basically just give the agent to a controller. And I'm going to showcase to you guys how to actually do this, but I'm going to first showcase one agent problem that I've already given this thing, and let's see how I can solve it and create new. You can see new neural networks created. The neural network is neat, Neuro-evolution of augmenting topologies, but in any future version I'm going to make it so that you can pick between neat or L-man recurrent and 50 generations. So these are the species that are created. This is the neat brain. This is what it looks like right now, but you're going to slowly see it evolve over time. Once the last car dies, more cars get spawned. Well, the point is for the cars to be able to complete this racetrack that's over here. Each of these cars have, let's see, you can see that here there's like, there's actually 31 input neurons. 15 input neurons are long distance LiDAR sensors, but essentially it's just like getting a distance to the wall that it's touching. And another 15 are short LiDAR distance sensors, so that means they can only see, they can't see as far as the other 15. And then the last one is a bias neuron. Oh wow, okay. The fitness just went up to 4,000 from 63, so that means one of these cars just figured out how to drive properly. Oh, I guess it's this car. Nice. Well, I mean, literally, it only took, oh, I think it crashed here. It took about 5 generations to be able to almost go around this lap. So neat is a pretty powerful algorithm. As you guys can see, it won't take very long before they can completely go around this turn. This is probably the hardest part. The current population is 60. You cannot change that at runtime. You have to change that when you first start. I already have a car saved which can go around this track, so if these guys don't evolve quickly enough, I already have one saved that can go around this. But suppose I want to save these cars. I want to call this car 1, and I'm just going to click save current and saved car 1. So that means car 1 is now saved into a file, and we can just load car 1 anytime we want. Well, when we first start the application, we can just type car_1 and then database load. It's actually not loading from a database, it's loading from the file like I stated before. That's what the system has been changed to, but if you want to set up a database, you can do that by yourself. The code is still there, and I'm also going to release the PHP code which takes that and saves to a database. You just have to create your own tables yourself. Well, this is taking way too long. I'm just going to show you guys the car that I've already saved which can go around this track. So I'm just going to load a car that I already know can go around the track, and it's called map1car that I already have saved. And I'm going to click the database load button, create new, and you can see that it says neural networks copied from sample, which is the sample file map1car. You can see that they all have the same color because it's just one car, right? It belongs to the same species. What the hell just happened? What? Oh, my bad. I accidentally set the test time to 12, where I actually wanted the population time to be 12. I think the test time was 60 seconds. Okay, I'm going to load it again. Map 1 car. Database load, create new. Timescale 1, 50 generations. So this is what the brain looks like. These red dots over here at the bottom are the hidden neurons, and they are generated because this algorithm is neat. Neuro-evolution of augmenting topologies. The hidden neurons are generated by random chance, and then the connections to those hidden neurons happen by random chance, and then eventually what you get is a neat brain which can actually solve the problem. Interesting, you can kind of see that the fourth and fifth neuron, for whatever reason, don't really have any connections. That can also kind of happen sometimes. We can see the fitness actually even skyrocketed from the previous. That means some of these cars can go around this track even a second time. As you just saw that this car actually slowed down a little bit as it was coming around this track. Oh my god, okay. So that car is pretty much the best car now, and I think I'm gonna save this. I want to override the previous map 1 car with this new map 1 car, which can actually go around the track twice without making any mistakes. So I'm going to click save current, and map 1 car has been overridden by this new better neural network. So now I'm going to enable the sensors now, so you can actually see the car making decisions based on its sensors. So that's just making this true. I apologize, I think I said that 15 of these sensors were short distance and then 15 were long distance, but I think it's that 15 sensors are just normal long distance sensors. The other 15 are actually the angle that the sensor is hitting the wall with, and this actually helps it navigate sharp turns a lot better than if it wasn't getting that information. The car could still learn it over time, but it would just be a lot harder. And there's some issues. I'm not sure what the issue is here. Why the sensors can just go past these walls when they really shouldn't be able to. I'll figure that out later. I'm just gonna guess that eventually the car will learn to use its left side of its sensors if it can't really trust the right side as much. I'm actually kind of interested. How did that other map 1 car able to do it? Yeah, I guess it just learned to trust its left side more. That's pretty interesting. Even with that kind of noise where some sensors really can't be trusted, this car's still able to learn to trust, I guess, the majority of its sensors given a situation. I think that's actually a testament to how good NEAT is for these kinds of problems. Now let's try out a completely different map. And now you guys can see some more information. These cyan boxes here are essentially tracks. The car gets, that's how the fitness is basically calculated. The first track that it spawns on is 1 fitness, and then 2, and then 3, and basically just keeps, it's basically just squared plus 1. That's how the fitness just keeps going up. Oh wow, okay, well, as we were talking, in just 4 generations it's able to get 63 fitness. It's really not going to be very long before it's able to complete this track. It's not going to be long before it can actually complete this course. They've gotten pretty good at turning towards the... gotten pretty good at making a U-turn towards the right. But I guess. Not very good at making U-turns towards the left. Oh, that was the first attempt at making a U-turn towards the left. $255 fitness. So it was actually taking a considerable amount of time to be able to go around this bend. So I kind of increased the size of this wall, but that really didn't help much. I only increased it just because I thought maybe if they go around this bend they would have to slow down just a little bit more, because it seemed like whenever they were coming around here they were going really fast. But I still had to run it for a little bit longer on my second try, but one of the neural networks finally learned to slow down and actually go around with a little bit of caution rather than just speeding and hitting this wall over here. So I've saved this neural network now, map2 car. Thankfully, I finally have a neural network that can go around this bend. And actually, going to be honest, this is the first time I've seen a car actually go around this bend. Usually they always crash. Finally, after about 60 or so generations, there's finally a species of cars that's able to go around that bend. And by the way, I tried controlling a car and driving it myself. It's really difficult. It's not easy at all. I kept crashing into the walls. I mean, the level of precision that's needed is quite high. So this is actually very impressive to me. Now let's move on to racetrack 3, but first of all, this is what the brain looks like. Not even using one. It's not using the first sensor at all, which is kind of funny. Oh wow, okay, this is a much more complicated brain. But you can see that the first neuron is not being used at all in this species, which is, I guess, kind of interesting. This track is kind of simple. It's just a bunch of really sharp turns that the car has to make. And the track basically just ends over here. Once the car gets here, it's immediately killed. It should have very high fitness if you can get to that point. Instead of starting all over again, I'm just going to load up the agent that we just trained, map2 car. So instead of starting from scratch, why don't we just use the agent that has just learned to be able to do quick turns, and then it shouldn't take very long for this agent to be able to learn to complete this map also. Let me go into orthographic projection mode. I think it looks a lot cooler to be in orthographic. Yep. This is like the 3rd generation, and I think it completed it. Wow, that didn't take long at all. Let's see, 4 generations and it's able to complete this track. I'll save this as map3 car now. Makes things a lot easier to train if you already have a preset, I guess, neural network that has already learned some basic tricks about your environment. So rather than starting from scratch, you might as well start with what you already have. So just to show you guys, this is actually kind of difficult. Driving this is not easy at all, especially doing high-speed turns around these corners. I'm going to try to stay in control while going fast, and I've crashed. I wonder how many attempts it will take before I can do this. Okay, I crashed there. That doesn't count. If I crash, I have to start again. I think I'm getting the hang of it. Okay, I guess not really getting the hang of it. I will, this time I got this. Okay, well, instead of booking it with full speed, I'm going medium speed. Alright, so that took about 5 or 6 attempts, not bad. So to create your own agent problem, I'm just going to give you guys an example of the boomerang, but this time we're actually going to code it with this program. So first thing that I want you guys to do is go into scene and open up the template scene. Just double click it. It's actually very useful because I already have the controller set up here, and the controller is basically the main logic of the thing. You have an agent problem, which is actually just going to be a game object with some script that you write, and we're just going to pass it to this controller, which through this test prefab, and essentially the controller will then just take care of spawning the things, and then the agent will just go around its environment that we're going to set and try to get some fitness. And then once the agent is done, the controller will take the neural network from that agent and essentially just rank it. Currently it's using shared fitness to propagate new neural networks in the next generation. And open up in the agent problems, you'll see a folder called template. Just open up the template.cs file. So this template.cs file actually I have set up, just takes care of all the little details that you don't have to worry about. So I'm just going to go through some of these methods, and I'm actually going to tell you which methods you actually have to write your code in. So first of all, the set color method is the color of your species, what we can see visually. The start method comes with the mono behavior automatically with Unity. Update network. This is where we're going to update our creature's behavior based on what the neural network predicts. The fail check, if there's some condition that you want your agent to fail in, you can just write that here. Calculate fitness on update tick. So on every update tick, you want to update the fitness. Calculate fitness on finish. So when the agent is finished, you don't have to worry about this fixed update. Generally, you would have had to write the code in here and fixed update, but you don't have to worry about this anymore. You don't have to worry about this either. This on finished, essentially it's just subscribing to a event listener in the controller. You can see over here in subscribe event, we're subscribing to an event in the controller, which is listening for agents to finish doing their tasks. You don't have to worry about any of that. You just have to write your code in these six methods at the top. Everything from mutations to reproduction, those kinds of things will just be handled on its own. You just have to make sure you've written the correct code in these 6 methods. Now let's create the same boomerang agent that we created in the previous neural network tutorial video, but I'm actually going to show it this time. So first of all, once you have the template scene open, just click File, Save Scene As, and we're just going to call this boomerang so that we don't mess up the template. Now go into Agent Problems and create a folder called Boomerang. In Boomerang folder, let's create a script called C#. Let's create a C# script called, well, Boomerang agent, I guess. We'll just call it Boomerang. But hope I'm spelling it correctly. Just open up the Boomerang script, and we're just literally, oh my god, what's happening here? Once you have the Boomerang script, once you have the Boomerang script open, just go into your template folder and copy everything that is inside the template class. All 140 lines of it, and paste it in the Boomerang script. There are some errors. Why? Oh, okay, right. So we have to import something for event arguments, which is just import using system at the top. The errors should go away. But once we're done doing this, let's create our Boomerang game object in Unity. I think the boomerangs looked kind of like a V shape, so I'm just going to create a 3D object. It's going to be a quad. Move the object to 0, 0, 0 so that we know where 0, 0, 0 is. Essentially, I'm just going to call this Boomerang Part 1. and then copy paste to make boomerang part 2. Essentially this is just going to be, the first part is going to be the first left side of the boomerang, and then the part 2 is going to be the right side of the boomerang, and they're going to combine together to make a V shape. We remove the mesh collider from both of them, so I want them to have scale on the x-axis 0.25. Let's make it 0.3, and then I want them to be quite long, so 1.5. The first part I want it to have an angle of negative 45 degrees. And the second part I want to have an angle of 45 degrees. And I'm just going to align these two together kind of manually. But that's how they're going to look, like a V shape. They kind of look like a boomerang now, right? So let's create an empty game object and call it boomerang. Make sure the empty game object is at 0, 0, 0. Give the empty game object these two boomerang parts, and give this new boomerang our boomerang script. Okay, so to this new boomerang component, add a physics 2D rigid body. So it's gonna have it's gonna have some physics so that it can rotate around. Basically, the neural network will control this rigid body, and save this boomerang object in our boomerang folder. I think that's pretty much it for this. Now go to the controller, which is at the top, and just pass this boomerang object to this test prefab. We're gonna change the number of input perceptrons and number of output perceptrons. I don't know why I used to call them perceptrons a long time ago. And we're gonna change the population size and all that. Once we're done coding the boomerang script, we have to add another little thing, which is go into assets, create sprites, and let's create a hexagon. Just drag and drop your hexagon into the scene, and essentially this is what our boomerang is going to try to get to. So the boomerang is going to be spinning around, but it's going to get very high fitness if it can get close to this thing. So eventually it should learn to track this thing. Okay, that's our task. I'm just going to give it a different color so it looks cooler. I think this is good enough. I'm just going to leave the name as hexagon because our boomerang script is actually going to try to find this hexagon using GameObjectFind in our code. So now open up the boomerang.cs file. Let's go into the start. First of all, we need to make a transform. And this transform is going to be for that hexagon, right? We need to get the transform component of the hexagon so that we know where it is in world space. So let's call this hex. In our start code, we're actually going to get hex. So hex is equal to GameObject.find. So we've found our hexagon and we know we have this object now. Obviously, if we named this hexagon something else, then this would have returned null. But I think we can be 100% sure that the hexagon exists since we just made it. Let's actually set the color to this thing now. So how are we going to set the color to it? Well, first of all, realize that the color has to go to the main boomerang script is in the boomerang game object. So the color has to go to the two child components of this boomerang, right? Let's get some rendering components. So renderer. It's going to be an array of child components. I believe it's get components and children. And the component that we want to get in the children is renderer. So now we can actually iterate through these child components. And once we're iterating through these, set the color, just go renderer, the renderers at the index dot material dot color is equal to the color. The color function is actually being called by the controller. So the controller is saying, hey, this is the color for the species that this agent belongs to. Do whatever you want with it. We don't have to color the agent, but we want to color them because it looks cool. Now we have the hexagon, which is in world space that our agent wants to follow, and we have colored our game object. So we don't have to worry about these two functions ever again. Let's move on to the update network. Our agent will essentially have one input and one output, and the input is actually going to be completely independent from the distance. I know I stated before that the fitness of the boomerang will increase as it gets closer to the hexagon. What we actually want to calculate the fitness on is not based on the distance, but rather based on the angle. If the boomerang is looking directly at the hexagon and we want it to have a very high fitness, not looking at the hexagon, we want it to have a very low fitness. So something kind of like this. If the boomerang is looking at the hexagon, you can see that it's looking right up at it. We want it to have a very high fitness, whereas if it was looking away from the hexagon, like away, we want it to have the lowest fitness. So first, let's create a float array of input, one input, solution to figuring out what input we want to give to the neural network. It's going to involve just a little bit of math, but just bear with me. First thing that we want to do is actually get the angle. So what we actually want to do is do %360. And sometimes the angles you can give back it's negative, but we don't want negative angles. So this way we are sticking between 0 and 360. Next thing that we want is actually a normalized vector between the boomerang and the hexagon. It's the angle of the two positions. If you were to draw a line between the two, what would be the angle of that? So first thing that we need to do is get a delta vector, and we want a normalized delta vector. So now we have some idea about the heading relative to where the hexagon is for this boomerang. Next thing that we want to do is actually get the angle of this delta vector, a tan 2. And we pass it delta vector.y and delta vector.x. So this delta vector angle that we've just returned of that line is actually in radians. I don't want to deal with radians, so radians to degrees. Next thing, let's just make sure, similarly to up here, that the delta vector angle that we've gotten back is between 0 and 360s. Next thing we need to do is actually subtract this thing from 90 degrees. The hexagon is actually pointing up, sort of vertically rather than horizontally. Otherwise our horizontal and vertical, the fitness will be switching places, and we don't want that. Once again, if our delta vector is less than 0, make sure you add 360 to it. Next thing that we need to do is make sure that our delta vector, which is now somewhere between 0 and 360, is actually switching places with its opposite location of the 360 degrees. So delta vector angle is equal to 360f minus, and this is going to set up for delta vector minus equal angle. Just making sure that when we're looking at the hexagon, we have the lowest possible angle, whereas if we're further away looking the other direction, we have the highest possible angle. And the highest possible angle is obviously going to be 180 degrees, because as you turn the other way after the 180 degrees, you start decreasing the angle. Right now, if it was facing this properly, it will have a degree of 0, because it doesn't need to turn anymore to be facing the boomerang. But as it starts turning, it needs to turn 90 degrees to face the boomerang. Here it needs to turn 180 degrees to face the boomerang. But here, let's suppose it was facing this way. If we stated that it needs to turn 90 degrees, it would actually end up turning this way, right? So when it's on this axis, on the left side, or the right side, sorry, it needs to be negative 90 degrees, so that it knows that negative 90 degrees means turning left, or negative 90 degree means turning right. So that way it can have that cardinality information, so that it knows whether it's facing towards the left or whether it's facing towards the right. So which way does it actually need to turn to face the hexagon? So if delta vector angle is greater than 180 degrees, then what we actually want to do is delta vector angle is equal to delta vector angle minus 360f. So now half the angle is going to be positive 180 degrees, the other half is going to be negative. What we want to basically do now is just delta vector angle is equal to delta vector angle divided by 180f. We want to divide this by 180 degrees because we want it to be between -1 and 1. And this is going to be a lot easier for our neural network to deal with. So the input will essentially just be 0 is equal to delta vector angle, which is now between -1 and 1. We want to calculate an output, and we have an output now from the neural network, and with this output we can actually do something to our rigid body component. One thing that I forgot to do was actually get the rigid body. So now let's go back up here. We actually need to declare another variable called rigid body 2D, r body, rigid body 2D. So it gets the rigid body 2D component that's attached to this boomerang. Now back down here, let's go rigid body dot velocity is equal to transform dot up. So which way is this boomerang facing? The direction, 0.5f. So it's always going to be going at that speed at whatever direction that it's facing. You want it to be able to control its angular velocity based on the output. So it's going to be churning at some speed based on what the output to this neural network is. So now that we've set now that the neural network is controlling this game object, we need to actually now give it a fitness. I'm not going to write my fitness in these functions because, like I said, you can use them or you don't have to. I'm just going to write it here because our fitness is actually going to be based on this delta vector angle. So we're going to do net dot add net fitness. As our delta vector angle approaches 0, we know that it's getting closer and closer to looking at the hexagon, and if it's looking at the hexagon, it's obviously going to be moving towards the hexagon, obviously, right? So we wanted to give it the highest fitness, which is going to be 1 minus 0 is 1, but if it's looking the furthest away, it's going to be the absolute of delta vector angle is going to be 1. 1 minus 1 is 0, so it's going to have no fitness added to it. So essentially the cumulative addition of fitnesses, if it's looking at the hexagon, the fitness should continue increasing. Let's give it a shot. I hope this works on the first try. So now what we need to do is actually set up our controller. So the number of inputs is actually going to be 2, not 1, because we have to add 1 for bias. So the first input is the normal input to the neural network and 1 bias. And the number of outputs is just going to be 1. The angular velocity. Our population size, let's make it 100. The test time is going to be 10 seconds. The elite 0.1, beta 1.5, remove 50% worst. The delta threshold disjoint really doesn't matter because this is a very small neural network. They should be able to solve this fairly quickly. Let's just start this now. Create in 50 generations. Okay, I think we might have to move this hexagon quite far. Oops, it looks like some of them already have a fairly decent idea on how to solve this. They're already following this hexagon, you can see. Yep, these guys have already solved it. We can see that over many generations, many of them have slowly started going over to this hexagon. Let's increase the time scale to 5, so it's going super fast. Well, yeah, I'm pretty sure they solved it literally in the first generation. But this is what the brain looks like. You can see it's kind of complicated. I'm really not sure what it's doing to solve this problem, but it seems that many of them are not even using the bias neuron at all. But we can see that the fitness is continuing to rise. It was 431, but now it's at 437. And it seems like the entire population have practically now solve this problem. They're all heading over to the hexagon. Yep, it's the entire population except for a few oddballs which have bad mutation. And that's it, really. I mean, you could now create any agent problem that you have and get this thing to try to solve it. Most of the hard work is already done for you by yours truly. You just have to write a decent agent problem and see how it solves it. You can now save this as boomerang1. Save current. Now let's see if we can actually load boomerang1. Database load, create new, loaded samples, perfect, 1, 50 generations. You can see that they're all the same species, pretty cool. So I just want to say some final things about this project. All the main files for NEAT can be found under the NEAT folder. These are all the files that you really need to look at if you're interested. So one thing that you can't code in that boomerang file is how you want to spawn your boomerang objects, like, you know, in a grid format, or do you want them to spawn in a circular format, you know, these kinds of things, like how they get spawned on the map and what orientation they're facing. That part has to be done in the controller itself. So if you go into the generate population method, you can write your own way of spawning them. So currently there's 2 ways of spawning it that I've set up, basically based on the spawn in grid variable. So if spawn in grid is true, then essentially it spawns them in kind of like a square format. If it's false, they spawn in the same location. If the random angle variable is true, then they spawn with different orientation. And if it's false, they spawn in the same orientation, meaning they're facing forward 0 degrees. So you can change this here. This is the only part this is the only time you should really have to come in this NEAT genetic controller class if you want to set up how you want to spawn them. So now if you want to change up how the species is calculated for the next generation, so if you want to change how these creatures are calculated, like what's the number of creatures per species, because currently it's using shared fitness, you have to make changes in the species class and this method generate new generation, and in the population class get distribution. You can currently see that in database operations, file save mode is true, saving to a file, but if it was false, doing a post request to this insert page. The PHP code will also be in the description with the project. So if you had an Apache server running and then you had some MySQL database, you could actually save it to a database. But for people who don't want to do that, just leave this true and the save system will work as it is right now. Last thing, essentially, those update net unfinished calculate is all based on this interface, iAgent tester. You can add more interface methods to this if you want. I made a video on this a long time ago, but I never really talked about it. I think it's just had some music on the projects. You'll find there's a scene called Racer AI. It's this project. I've already made a video on this and the link will be in the description, or you can just go through my videos and find this thing. In the previous video that I made, it did not have speciation. I don't remember what algorithm I was using. I'm pretty sure it wasn't shared fitness, it was something else. But yeah, they usually solve this thing pretty much on their first try. So this is one of the maps. Let me show you guys the other maps. I think I never actually showed this map in that video. This was supposed to be one of the harder maps that I wanted them to be able to learn, but it turned out to be practically a joke for them because they all solved it in the first case. And that's when I basically ended up making that other green looking map because I wanted it to be a little bit more difficult. Here's another map that I didn't showcase in that video. I just took this from Google and basically went and made edge colliders. And this bend here was supposed to be the hardest part, at least I thought that it would take them quite some time to be able to solve this, but it turns out it's quite easy. Now in 3D, what I already showed at the start of this video, it's actually quite difficult for those cars to do it because they have acceleration, and these guys are just using normal velocity changes. I mean, they can change their velocity on a whim. That's why it's so easy for them to complete this. And finally, because it was so easy for these agents to solve this problem, I thought might as well make it a little bit more difficult with actual obstacles around them, and then seeing how much more difficult that is. But it turns out even this problem is quite easy to solve. Here's another map, but I'm not going to show you. You guys can try that out yourself. So basically this is under Racer AI.Unity scene. So that's pretty much it for this video. I hope that this project makes up for not putting out a video for a month. Definitely let me know if you guys use this project to solve any specific problems. And if you have any questions regarding this project and you want to solve a specific problem and you don't really know how to do this, or if I didn't do a very good job in explaining this project and how you can configure the controllers and that kind of thing, definitely let me know in the description and I will answer them. Other than that, thanks for watching and see ya.